Hello everybody, this is Miss Peachy with your WCA Physics class again. And today I'm going to do a little tutorial to talk a bit about these, basically what they are one-dimensional motion problems. So they may call them like displacement with constant acceleration or any kind of, determining final velocity after displacement. You'll see these in your lessons starting with like lesson 3 and even into lesson 4 when you're getting into free fall. So all of these kind of go together. In my last video, I was kind of showing you how you derive some of these equations, and we went through a little bit of where they came from because they're essentially using equations for velocity and for acceleration and combining them in different ways to solve for different variables. Remembering that velocity is change in displacement over change in time, and acceleration is change in velocity over change in time. So if we combine some of those equations, we come up with all of these different options here on the screen. I'm going to try to get this a little bit closer so you can kind of have a better view of this. Slightly larger on the screen for you. Now, I wrote these all down at the top of my paper, but I want to direct you to my website. So if you haven't checked out the physics website yet, make sure you do that. You go to the message boards, that pushpin icon at the top of your screen, and click on it, and then find your physics section message board. And when you follow the links, it will give you the link to my Google site. Then I would recommend that you bookmark that link. Just today, I put an image at the top of the screen of the physics page on my Google site that has all of these equations there for you, and they're written a little bit nicer than I wrote them here. These are very important. You'll be using them all the way through the rest of this unit and all the way into the next unit as well, and really kind of periodically throughout physics. So for this unit, what we're doing right now is sometimes called one-dimensional motion. And believe it or not, this is way easier than what we're going to do in the next unit, which is two-dimensional motion. So think about it. Most of the time, you're not moving in one dimension, right? But what we're looking at is just stuff that moves back and forth or up and down. Only one of those we're focusing on at a time. So either back and forth or up and down. Okay, so we're just looking at, when you look at the different dimensions, and you look at, a Cartesian coordinate system, we have our X and our Y. To start off with, we're just looking at motion in the X direction, which is kind of that horizontal motion back and forth. Towards the end of this unit, we're looking at things that are falling. And when you're falling, they're just moving in the Y direction. Straight up just falling, not like being thrown or anything like that. That actually, when you look at something that's being thrown, it has both X and Y motion. That's the next unit that we'll be doing. So right now it's either just X or just Y. So it makes it much simpler, even though I know some of you think it's very complicated right now. Hopefully I can clear that up a little bit today, but we'll be combining those in the next unit. So these are the different possibilities. And I just want to remind you of what some of these things mean, right? Delta means change in, and we have those little subscripts that refer to initial and final and that kind of stuff. So here we have the first equation here. These, by the way, these are often referred to as our kinematic equations. So you'll see these classically referred to as kinematics or kinematic equations. You'll see that term. They mention it in your lessons, so just so you know. The stuff there on the left, these are essentially the ones you use for something that does not start from rest. So it has an initial velocity. If the object is starting from rest, we don't have to worry about v sub I because there is no initial velocity. So those equations are a little simpler. They've been simplified to eliminate that v sub I. Otherwise, they're the same equation. You see here, if this is 0, well, then you just have v sub f equals a delta t, because that part is plus 0. So kind of just get rid of it. They're the same equations exactly. We're just already getting rid of that v sub I for you, just so you know, okay? So here I have a question, and we're going to look at how to use this. This is like one of the problems that you may have to work out. So a plane starts from rest at one end of a runway and then undergoes a uniform, remember that means constant, acceleration of 4.8 meters per second squared for 15 seconds before takeoff. What is its speed on takeoff, and how long must the runway be on takeoff? We don't want it to fall off the end of the runway. So let's look at our givens here, and then we'll also look at what we want to know. So you're always going to start off here looking at your givens. So we were given that it's taking off, so its initial velocity is 0. Its acceleration is 4.8 meters per second squared. We know that it's accelerating for 15 seconds, but we don't know how fast it needs to take to be on takeoff. That's an unknown, right? And we don't know how long the runway needs to be. So we don't know delta t, and we don't know v sub f. These are the things we're trying to figure out in this particular problem here. So this is going to be kind of a two-step problem. We're first going to solve for one of the variables and then use that to help us solve for the second variable. So the first thing we're going to solve for is the final velocity. Okay, so final velocity, we have an equation for final velocity up here where we use the initial velocity plus a delta t. Well, we don't need to worry about initial velocity, remember, because it's starting from rest. So we're actually going to use this one. Again, these are the same equations, it's simpler over here. So let me start off by solving for v sub f. So v sub f equals a delta t, right? Because we know these things. We know a and we know delta t. So that's an easy one to solve for. So let's continue with that. V sub f equals 4.8 meters per second squared times 15 seconds, right? So we know that the seconds here cancel out, and then one of the ones at the bottom will cancel out. And we'll do 4.8 times 15, which gives us 72 meters per second. So that is our final velocity. So now that's a known. Now we know what that one is. And now I need to figure out how long of a runway I need. Okay, so I need some equation up at the top that is helping me solve for delta x. And at this point, you pretty much know every other variable, so you can pretty much pick any one of them up there that's solving for delta x. I kind of like, if possible, let me just check these guys out a little bit. I kind of like to stick with the ones that don't rely on the answer you just got, if possible, okay? So like we just solved for this, but if I made a mistake here in some way, if I use this number to try to solve for the second part of my problem, then that mistake carries forward. So if possible, and it's not always possible, I'm going to try to avoid using this to solve for delta x, if possible. I do see one equation that allows me to do this up here. Delta x equals 1/2 a times delta t squared. I have all that other information, so I don't need to use the v sub f if I don't have to. So we're going to use that one, okay? Delta x equals 1/2 a delta t squared. That's the equation. Delta x equals 1/2 times 4.8 meters per second squared times t is 15 seconds. And I'm going to square that. So remember your PEMDAS, right? Please excuse my dear Aunt Sally. Your order of operations. We're going to start with the exponent. So we're going to square that 15 first. Okay, so 15 squared is 225. So I'm just going to rewrite this here as 225 second squared. Okay, now I'm going to multiply it by 4.8. Meters per second squared. And now here the second squared is on the numerator and here the second squared is on the denominator. So those will cancel, right? Just cancel those out with my pencil. Gotcha. So the only unit I have left is meters. So I'm going to take 4.8 times 225, which is 1,080. And then I have to multiply it by 1/2, which is the same mathematically as dividing by 2. So I'm going to divide that by 2, which gives me my delta x is equal to 540 meters. Okay. So my final answer here is the plane needs to be traveling at least 72 meters per second. Remember, meters per second and miles per hour are not the same thing, so it might look really slow, but it's actually much faster than you think it is. And then it needs to be traveling for a minimum. It has to have a runway that's a minimum of 540 meters long. I would hope the runway would be longer because that would be kind of scary if it went all the way to the end of the runway. But it needs to be a minimum of 540 meters long. Okay. Now, you could have used other kinematics for this, ladies and gentlemen. It doesn't matter. You certainly could have used this first one and use that 72 meters per second to help you solve for it. That was acceptable. You could use that. I mean, you could really use this last one if you wanted to and solve for delta x. So you could use any one of these. If even this last problem here, it's not already arranged to solve for delta x, but you know how to rearrange an equation and solve for a variable. So you can use that. So if we didn't have time, sometimes they'll give you a problem where they don't give you how long it is. You're going to need to use maybe this one because it does not have delta t as part of that equation. Okay? So that is kind of one of the examples of using kinematics in the x direction, for straight line motion. The other section you have has to do with free fall. So with free fall, okay, so free fall, remember, is when an object is falling and it's not kind of given any initial force. It's not at all being thrown, it is just dropped, okay? This means that gravity is pulling the object down, and gravity has a constant acceleration of negative 9.81 meters per second squared. Remember that it's negative because it is being pulled down. Okay, so it's being pulled down. We call it negative in this situation. So anytime you see an A in your kinematics, you're going to be substituting negative 9.8 meters per second in for A. Okay? The other thing is that with your kinematic equations, you can use any of the kinematics we already kind of talked about. Whenever you have to solve for delta, what it would normally say solve for delta x, you're just going to put delta y in that case. It doesn't matter if it's in the x direction or in the y direction. Any one of those is fine. All right, so now we're going to kind of look at a problem with this free fall motion, okay? So here I have the same equations I had on the previous sheet. As you can see, I kind of just flipped it over here. It's like a flip book. And I have our problem. So here we have Jason. Jason is hitting a volleyball, so it moves upward with an initial velocity of 6.0 meters per second straight up. If the volleyball starts from 2 meters above the floor, how long will it be in the air before it strikes the floor? Okay, so we want to know the time it takes to actually come back and hit the floor. Let me talk to you a little bit about reference frame here. So we're going to use the volleyball's initial position as our 0 point in our reference frame. So if we think about this as the floor here, right, then the initial position of the volleyball right here is the 0 point of our reference frame. And that is 2 meters above the floor, right? So 2 meters above the floor is 0. So when it hits the floor at the very end, it's actually at a position here, right here. This is our y point, is going to be negative 2 meters. Does that make sense? Starting at 2 meters above the floor is considered to be our beginning point, our starting point. So when we're hitting the floor, that's now 2 meters below where we began. So our delta y in this case is a negative 2 meters. That's one of our knowns. Delta y is negative 2 meters because we're looking at its ending spot on the floor, which is 2 meters below where we started. The other things we know here is we know our initial velocity of positive 6.0 meters per second. We also know acceleration, which is always in free fall going to be a negative 9.81 meters per second squared. That's acceleration due to gravity. What we don't know is we don't know the time. That's what we're looking for, right? Delta t is an unknown. The other thing we don't know is we don't know the final velocity of the ball. I should say v sub f. We don't know that either, okay? So in this situation, we have two unknowns, really, and so we're not able to directly use one of the equations to completely solve it. We need to know delta t. That's what the problem's asking for. And in no situation where we have an initial velocity can we solve for delta t unless we also have a final velocity. So we have to know the final velocity too. Does that make sense? You need to know both. You need to solve for final velocity before you can solve for delta t. So remember, any of these situations here, I just substitute a y in there for x. So I'm going to use that equation there. I'm going to use v sub f squared equals v sub I squared plus 2a delta y. Same equation, I'm just looking at a different dimension, the up-down dimension rather than the back-forth dimension. So I'm going to solve here for v sub f. So I'm going to substitute in here my v sub I, the 6 meters per second, and I'm going to square that, and plus 2 times negative 9.81 meters per second squared times negative 2 meters, right? So it really doesn't matter which side I do first. Let's do 6 times 6 is 36. So we'll do 36 meters squared per second squared plus negative 9.81 times a negative 2. My calculator got buried. Really, the negatives cancel each other out, right? Negative times a negative is a positive. So I'm just going to ignore them in there. So that's plus 19.62. And then I'm going to multiply that times 2. Okay. Sorry. So that's 39.2. And meters times meters is meters squared per second squared. Excuse me. And then I'm just going to add these guys together. Okay. Sorry, did that off camera, but you got it. Just adding 36 plus 39.2, which gives me 75. I'm just going to round it to 75 at this point because I've been making so many rounding. I've been rounding so many times. I just don't want to just keep rounding and rounding and rounding because it gets to be a little inaccurate. So meters squared per second squared, and that is equal to V sub F squared. So I take the square root of both sides. Square root of 75 is 8.7. Yeah. Now this is, remember that we are actually traveling downward at this point. The final velocity is going downward. So this is going to be a negative. I'm going to add that negative side on there because at this point the ball is actually moving downward. So it has a negative final velocity. Okay, even though when I did the square root, it's a positive number, we have to remember directionality here too. Make sense? So that's where that negative comes into play. It's really, really important, everybody, to make sure you're paying attention to your signs because that can mess up your whole equation if you're not. Think about where your reference frame is. This is what we did here. And then make sure, when you're doing velocity that you know which direction the object's traveling. Initially, it was traveling upwards. We used positive, so downward has to be negative. Then the second part of this, remember, we're still solving for delta t. Now we have final velocity. So I can use any one of these equations up here to solve for delta t. This one's actually a pretty easy one to use here. I think that's probably going to be my easiest one, so I'm going to use that one up on top. Excuse me, got a little frogger in the throat there. So the equation is final velocity equals initial velocity plus a delta t. And I want to solve for delta t, so I'm going to divide both sides by a. Well, let's first subtract v sub I from this side. Excuse me, again. And so I'll have v sub f minus v sub I. And then I'm going to divide both sides by a to get rid of it on this side. So I do it on that side. And then this side is divided by a equals delta t. Okay. So let's see what we got here. So our final velocity we said is negative 8.7 meters per second. Minus our initial velocity, which is 6.0 meters per second. That's a positive. Divided by negative 9.81 meters per second squared. So let's see the top part here. We've got to at least simplify that first because this should be in parentheses here. Please excuse my dear Aunt Sally, parentheses first, right? So negative 8.7 minus 6. clear that out. 8.7 negative and minus 6 is, remember it's plus and negative, so that's negative 14.7. And then divided by negative 9.81 meters per second squared gives us a positive 1.5. We'll round it. And remember that the meters per second cancel, at least one of these seconds do. And it's actually like the inverse of an inverse. So you're talking about, it's like you have a fraction in the denominator, you move it to the numerator, right? So we have 1.5 seconds is how long it takes. So the ball is going to stay in the air 1.5 seconds and then hit the floor. Okay? So hopefully that makes sense. It's a two-step process. Sometimes you need a two-step process. Trust the kinematics. Trust them. They're there. They all work. So if you need to solve for a specific variable, like I said, you may have to do two different equations to solve for one variable and then use that to solve for a second variable. But trust those that they'll work for you. And really pay attention to the signs. If you're doing the free fall problems, if it's moving up, it's positive. If it's moving down, it's negative. If you're starting above the floor, like we are here, or above a certain point, anything down from that is negative, and anything up from that is positive for your delta y as well. All right, ladies and gentlemen, that's another practice problem, and that should kind of get you through with how to use those kinematics. If you need anything else, if you have any additional questions, feel free to contact me and I will try to help you out. Have a great day.